Okay, student. Now we'll continue the narrowband FM. What is the narrowband FM wave? Narrowband FM means beta is less than 1. So AC cos 2 pi FCT minus AC beta into sin 2 pi FCT into sin 2 pi FM into T. This is the equation we are getting, right? So this is the narrowband FM wave in time domain. You just divided with 2, multiplied with 2. 2 sin A, sin B. Therefore, S of T of narrowband FM, which is equal to AC cos 2 pi FCT minus AC beta by 2, 2 sin A sin B, cos of A minus B cos 2 pi FC minus Fn into T minus minus plus AC beta by 2 into cos 2 pi FC plus Fm into T. Now this is carrier, this is carrier, this is lower side band, this is upper side band, right? Now carrier, upper side band, lower side band. Now this is narrowband FM wave in time domain. Now we never see the frequency domain of narrowband FM and what is the bandwidth of narrowband FM. Okay. Now before we calculate the bandwidth, now let us take first power. Okay. What is the total power? The total power is nothing but power taken by the carrier component plus power taken by the lower side band plus power taken by the upper side band. Right? Now, what is the power taken by the carrier component? AC square by 2R plus all are analog signals, all are sinusoidal signals, continuous wave signals. RMS value is peak amplitude divided by root 2. AC square beta square by 4R. Oh, sorry, 4 into 2, 8R plus AC square beta square by 8R. The total power, which is equal to AC square by 2R plus AC square beta square by 8R, AC square beta square by 8R, AC square beta square by 4R. Therefore, the total power, which is equal to AC square by 2R, is taken as a common 1 plus beta square by 2. AC square by 2R is the carrier power. The total power, which is equal to PC into 1 plus beta square by 2. This is the power, the total power required to transmit, a narrowband FM. So, which is a function of modulation index, beta. Now, similarly, can you see the same power somewhere? So, if you see the power, the total power, which is equal to PC into 1 plus mu square by 2, this is the total power required to transmit an AM signal. This is also a function of modulation index. This is also function of modulation index, and this is the total power required to transmit an AM signal. This is in AM and this is in narrowband FM. Both are appears to be same or not? Function of modulation index, function of beta, function of mu. Carrier, upper side band, lower side band power. Carrier, upper side band, lower side band power. Am I not? Okay. Now this is the power calculations of a narrowband FM wave. Now we'll see the bandwidth calculations. S of F, this is narrowband FM in frequency domain. Now which is equal to AC by 2 into delta of F minus FC plus delta of F plus FC minus AC beta by 2, AC beta by 4 into delta of F minus FC minus Fm plus delta of F plus Fc minus Fm. Now plus AC beta by 2 becomes AC beta by 4 into delta of F minus Fc plus Fm plus delta of F plus Fc plus Fm. Now this is the narrowband FM wave in frequency domain. Draw the spectrum. Now F equal to plus Fc. F equal to minus Fc, whose spectral amplitude is AC by 2. Now F equal to Fc minus Fm. F equal to Fc minus Fm, but there is a phase shift. Fc minus Fm, minus 1 means 180 degrees. AC beta by 4. F equal to minus Fc plus Fm. Minus Fc plus Fm. Minus Fc plus Fm. AC beta by 4. F equal to Fc plus Fm. F equal to Fc plus Fm. AC beta by 4. F equal to minus Fc minus Fm. Minus Fc minus Fm. AC beta by 4. Now this is a narrowband FM. Narrowband FM spectrum. Narrowband FM. Now what is the bandwidth? Now the bandwidth of narrowband FM, the bandwidth of narrowband FM is Fc plus Fm minus of Fc minus Fm, which is equal to 2 FM hertz. What is the bandwidth of AM? 2 omega or 2 FM hertz. And narrowband FM is having 3 spectral components: carrier, upper sideband, lower sideband. AM is also having 3 spectral components: carrier, upper sideband, lower sideband. Total power is Pc into 1 plus mu square by 2. Total power is Pc into 1 plus beta square by 2. Now bandwidth is 2 FM and bandwidth is 2 omega. Bandwidth is 2 FM, bandwidth is 2 FM. So all are similar. Number of spectral components are 3. Total power equal to carrier, upper sideband, lower sideband power, and bandwidth is same. Because of all these similarities, the narrowband FM is not preferred practically because of its similarities to AM. Right? What is the major difference? What is the difference between AM and narrowband FM? The only difference between AM and narrowband FM is now this lower sideband in LSB, in narrowband FM, this lower sideband is out of phase by 180 degrees. Okay, that is a major difference between an AM and narrowband FM. Otherwise, everything will be same. Okay, no doubt. The total power equal to carrier power plus upper sideband power plus lower sideband power. So the total power, which is equal to Pc into 1 plus beta square by 2, and bandwidth, which is equal to 2 Fm. Now this is AM, total power, which is equal to power taken by the carrier, power taken by the upper side band, or power taken by the lower side band. Therefore, the total power, which is equal to PC into 1 plus mu square by 2, and bandwidth here is 2 FM. This is in amplitude modulation. Okay. So in narrowband FM is 3 spectral components. AM is also having 3 spectral components. AM is having 3 spectral components, which is equal to AC by 2 FC, FC plus FM, AC mu by 4, FC minus FM, now this is AM, bandwidth of AM, and this is bandwidth of narrowband FM. See these two parameters, 3 spectral components, and power equal to carrier upper side band, lower side band, carrier upper side band, lower side band, power and bandwidth. If you see, now because of these similarities, this narrowband FM is not preferred because of similarities to AM with respect to bandwidth, with respect to number of spectral components, and with respect to power. Okay, only the difference between AM and narrowband FM is in narrowband FM the lower side band LSB is in narrowband FM the LSB is out of phase by 180 degrees. In narrowband FM, the lower side band is out of phase by 180 degrees. Okay, this is the major difference between AM and narrowband FM. Okay, note down. Now see here, AM and narrowband FM signals, a small objective question. Okay, and AM and narrowband FM signals are having same modulation index, which is nothing but mu equal to beta. AM and narrowband FM signals are having same modulation index, which are added each other. Then the resultant signal is options I am writing here. Then the resultant signal is AM, DSBSC, C, SSBSC, D, none. Once again repeat the question. And AM and narrowband FM signals are having same modulation index, which are added each other, then the resultant signal is dash. See here, mu equal to beta, beta equal to mu, so not a issue. So both are added. So if you add carrier, upper side band, lower side band, but these two lower side bands are out of phase by 180 degrees. Therefore, these two are cancelled or not? This one and this one is cancelled or not? These two are cancelled. So what is the resultant signal? One side band, right? So single side band suppressed carrier. If you go for this option, which is 100% wrong option. Suppressed carrier, but here carrier is available. Both the side carriers are available. So one side band, one single side band, and one carrier, or upper side band with carrier. So what is the correct answer? Answer is single side band with carrier or upper sideband with carrier. This is the correct option. So if this option is not there, none of the above is the correct option. Okay, which is one important objective question which is already in the previous gate examination. Note down. Now see here. Now classroom workbook question number 2 in angle modulation. Narrowband FM. A message signal band limited to 10 kHz is lower sideband SSB modulation with a carrier frequency of 1 MHz. A message signal band limited to, first we'll see. A message signal band limited to 10 kHz. No diagram, nothing, okay? For easy understanding, I am writing like this. A message signal band limited to 10 kHz means a signal which is having a bandwidth of 10 kHz or a highest frequency present in this signal is 10 kHz. So a message signal band limited to 10 kHz is lower sideband SSB modulation. This message signal is lower sideband SSB modulation. SSB modulation, but lower sideband SSB modulation means, because single sidebands means it may be upper sideband or lower sideband, but he is mentioned strictly here. This is the lower sideband with a carrier frequency of 1 MHz. With a carrier frequency of 1 MHz. Then the output of this SSB modulator with a carrier frequency of 1 MHz, the resultant signal is again passed through a narrowband FM modulator. The resultant signal is again passing through a narrowband FM modulator. The resultant signal is again passing through a narrowband FM modulator with a carrier frequency of 1 GHz. Then what is the bandwidth of output signal? What is the bandwidth? This is the output. Let us assume this is the output signal. Now this is the bandwidth of output signal, which is nothing but bandwidth of narrowband FM modulator output is nothing but narrowband FM wave. What is the bandwidth of narrowband FM? Which is equal to 2 omega or which is equal to 2f hertz. Means what is omega? Omega is a message signal. Don't take this as omega. This is input to SSB modulator. So I want message signal for at here. Okay. So now what should we do? This is amplitude modulation. Let us assume this message signal is an amplitude modulation first. What is amplitude modulation? Now that 0 is at FC. That 0 is at FC 1 MHz. Now 1 MHz plus 10 kHz. 1010 kHz. Now 1010 minus 10 kHz, which is nothing but 990 kHz. Now that is for right shifting, and left shifting is, this is minus 1 MHz minus 1010 MHz minus 990 MHz. Oh, sorry, kilohertz. This is amplitude modulation. But what he is saying, now this is SSBSC lower sideband. Lower sideband. This is upper sideband. This is lower sideband. Okay. Now this side, this is lower sideband and this is upper sideband. So now SSB SC modulator with lower sideband. So first you take this one. Now SSB single sideband with LSB. Now with LSB, now this is LSB. This is LSB. Okay. Now this signal is here. Now this is input to the narrowband FM modulator. Now that is input to the narrowband FM modulator. This is 1 GHz. Now this spectrum is shifted at 1 GHz. Now this is the narrowband FM. What is the highest frequency now? This is the highest frequency. Okay, this is the highest frequency. But what is the bandwidth? The bandwidth is 2 omega because this is multi-tone. So 2 omega. Now highest frequency present in the given signal is 1 megahertz, which is equal to 2 megahertz is the bandwidth of output signal component, and with respect to power. So finally, angle modulation, which is nothing but wideband FM. Wideband FM. So what is wideband FM? But what is actually FM? Now this is the standard mathematical time domain equation of FM wave. AC cos of 2 pi FCT plus beta into sine 2 pi FM into T. This is FM wave. But here when beta less than 1, narrowband FM, approximations are available. Approximations are available. Approximations are available. Now this is S of T of FM, but when beta greater than 1, when theta is greater than 1, approximations are not possible. Approximations are not possible. When approximations are not possible, when beta greater than 1, approximations are not possible. So if the approximations are not possible, so we use, therefore we use Bessel function. We use Bessel function coefficient Jn of beta for reducing above equation. Beta greater than 1, approximations are not possible. So we use beta, Bessel function coefficient Jn of beta for reducing the above equation, this equation. So for better understanding, I can write like this: C of t, which is equal to AC cos 2 pi FCT plus phi. This is carrier before modulation. Why not? This is carrier before modulation. What is the amplitude of the carrier before modulation? AC. What is the amplitude of the carrier after FM modulation? AC only. There is no change in amplitude. Am I right or not? So cos 2 pi FC. What is the phase of the carrier before modulation? Phi. Phase of the carrier after modulation is also phi. There is no change in phase. So there is no change in phase. There is no change in amplitude. Right? Now, but the wideband FM and narrowband FM is separated by a Bessel function quotient. The Bessel function quotient is Jn of beta. Am I not? Jn of beta. So beta is nothing but modulation index we required. So summation n equal to minus infinity to infinity Jn of beta is the Bessel function quotient of order n. Now this is a wide band FM, wide range of frequencies, wide band FM. So this is Fc plus NFM into T. So if n equal to 0, Fc into T, n equal to 1, Fc plus Fm, Fc plus 2Fm, Fc plus 3Fm, Fc minus Fm, Fc minus 2Fm, and so on. Okay. Now this is wideband FM wave in time domain. This is the standard mathematical time domain equation of wideband FM. Now before we start the analysis of wideband FM, we just see some properties of this Bessel function quotient. Okay, note down this. Quotient is Jn of x. We'll take directly Jn of beta. Jn of beta Bessel function quotient of order n 1 by 2 pi integral minus pi to pi e power j beta sine theta minus n theta integrate with respect to theta. So if n equal to 0, beta equal to 0, so this is 0, e power 0 1, integration d theta is theta. So j0 of 0 which is equal to 1. Now summation n equal to minus infinity to infinity sum of squares of Bessel function quotient which is equal to 1 and j n of beta which is equal to minus 1 whole power n into j minus n of beta. Jn of beta which is equal to minus 1 whole power n into j minus n of beta. Now see here, if you take n equal to 1 here, if you take n equal to 1, j1 of beta which is equal to minus 1 whole power 1 into j minus 1 of beta which is nothing but j1 of beta which is minus j minus 1 of beta which is nothing but j minus 1 of beta which is nothing but finally j minus 1 of beta which is nothing but minus j1 of beta. Is it right or not? Now similarly n equal to 3, j3 of beta which is equal to minus 1 whole power 3 into j minus 3 of beta. So j3 of beta which is equal to minus j minus 3 of beta. Now which is nothing but j minus 3 of beta which is minus into j3 of beta. So what is the meaning of this? Finally what we conclude here, Now if you see here, from here what we conclude that for odd values of n, j minus n of beta, which is equal to minus jn of beta. For odd values of n, j minus n of beta, which is equal to minus jn of beta. Now similarly, if I write, if n equal to 2, j minus, if n equal to 2, j2 of beta, which is equal to minus 1 whole square, j minus 2 of beta, which is equal to j2 of beta, which is equal to j minus 2 of beta. Now similarly, if n equal to 4, j4 of beta, which is equal to minus 1 whole power 4 into j minus 4 of beta, which is equal to j4 of beta, which is equal to j minus 4 of beta. So what we can understand here, for even values of n, j minus n of beta, which is equal to jn of beta. Okay, note on this. These are the properties of this Bessel function. You can use all these properties while you are studying the operation of spectral analysis. Because now we need to find the bandwidth and power calculations. Now, fourth one is for constant beta. For constant, you fix some beta value constant. For constant beta, as n value increases, jn of beta is decreases. Clear or not? So for constant beta, as n increases, jn of beta is decreases. Therefore, jn of beta is less than j0 of beta, and j2 of beta is less than j1 of beta, like this, and so on. Therefore, jn of beta, which is less than jn minus 1 of beta and less than j, and so on, like this. Okay. Now these are the properties of the Bessel function coefficient for easy analysis of a wideband FM spectrum. So these are the properties of the Bessel function. Now we'll see the spectrum of wideband FM. Wideband FM spectrum, spectral analysis. Wideband FM spectral analysis. Now I first expand this equation. Okay. Now what is this equation? S of t of wideband FM, which is equal to AC n equal to 0, j0 of beta into cos 2 pi fct plus n equal to 1, if n equal to 1, AC J1 of beta into cos 2 pi FC plus FM into T. N equal to 2, AC J2 of beta into cos 2 pi FC plus 2 FM into T, plus and so on. Plus, if n equal to minus 1, AC J minus 1 of beta into cos 2 pi FC minus FM into T, plus AC J minus 2 of beta into cos 2 pi FC minus 2 FM into T, plus and so on. Okay. Now this is carrier, upper side band 1, upper side band 2, upper side band 3 and so on. Lower side band 1, lower side band 2, lower side band 3 and so on. Now first I want to find what is the total power. Now you tell me, the students, without calculating anything, what should be the total power you are expected. Okay, the total power required to transmit a wideband FM or FM, forget about the narrowband FM, only FM. So amplitude of the carrier before modulation is AC, which is constant. Amplitude of the carrier after FM modulation is also AC. Is there any change in the amplitude before modulation and after modulation? No. If there is no change in the amplitude before modulation and after modulation, definitely there is no change in the power. Envelope is not changing, then the power will be same. But in AM, before modulation carrier amplitude is AC, after modulation carrier amplitude is continuously changing. That's why the power is changes. But here before modulation AC and after modulation is also AC, definitely the power is same as that of the unmodulated carrier power. But if you have any doubt, we will check. So what is the total power? The total power, which is equal to carrier plus upper side band 1 plus upper side band 2 plus and so on, plus lower side band 1 plus lower side band 2 plus and so on. So the total power, which is equal to AC square by 2R plus AC square J naught square AC square J naught square of beta by 2R plus AC square J1 square of beta by 2R plus AC square J2 square of beta by 2R plus and so on, plus AC square, because all are sinusoidal signals, RMS value is power. AC square J minus 1 square of beta by 2R plus AC square J minus 2 square of beta by 2R plus and so on. So what is the total power? The total power, which is equal to, in all the terms, AC square by 2R as a common. Now if you take, this is J naught square of beta plus J1 square of beta plus J2 square of beta plus and so on, plus J minus 1 square of beta plus J minus 2 square of beta and so on. So the total power, which is equal to, AC square by 2R, this we can be written like this, summation n equal to minus infinity to infinity Jn square of beta, sum of squares of all the Bessel function coefficient value, which is equal to 1. So the total power, which is equal to AC square by 2R into 1, which is nothing but same as that of unmodulated carrier power. Now this is the total power required to transmit a wideband FM, which will be same as that of the total power required to transmit wideband FM. How much power before modulation? The same power is sufficient to transmit the signal after modulation. Okay, so the total power of wideband FM is same as that of the unmodulated carrier power. unmodulated carrier. How much power is required for unmodulated carrier? That much amount of power is sufficient to transmit the FM signal. Let us assume, for example, before modulation carrier power is 10 watts. After AM modulation carrier power is not 10 watts. It should be changed and it should be increased because sidebands are coming. But before modulation carrier power is 10 watts. After modulation, after FM modulation also, the carrier power remains same, which is 10 watts, because envelope will not disturb. Envelope will be constant. Amplitude will be constant. Amplitude before modulation, after modulation will be same. Therefore, the total power required to transmit a wideband FM signal will be same as that of unmodulated carrier power. Okay. Now, this is the power calculations of of wideband FM. Now, similarly, you tell me what is the power taken by the carrier? The power taken by the carrier is AC square J naught square of beta by 2R. It depends upon the Bessel function quotient J naught of beta. What is the power taken by the first order sideband? What is the power taken by the first order sideband? The first order sideband is nothing but AC square J1 square of beta by 2R plus AC square J minus 1 square of beta by 2R. This is the power taken by the first order. Now, which is nothing but AC square J1 square of beta by R. Okay. Now, similarly, the power taken by the second order sideband. The power taken by the second order sideband, which is equal to AC square J2 square of beta by 2R. Minus means plus itself. Therefore, square not a problem. AC square J minus 2 square of beta by 2R, which is equal to AC square J2 square of beta by R. Note down.